So, hi everyone. There is no live audience today, so you guys must be watching the recorded version. So, I welcome you all to this live session 7 of the course Digital Circuits. So, this is the first time I'm not having any audience here. This happens towards the end of the live sessions. So, what I will do, I'll just go through each problem slowly because in the live audience, I get a feedback from the students and taking help from that feedback, I can sometimes repeat the solution or explain few points. So since there is no audience right now, so what I'll do, I'll go through each problem slowly, try to explain it twice at least, and also explain all the steps. In live session, when we have live audience, we can skip some points, and even during some live sessions, I explain all the steps, but sometimes I can skip some steps. If there is some confusion, audience member used to point me out. But right now I don't have any audience member, so I'll go through each problem slowly. So I think I should start. I don't know why there's actually I was expecting at least a couple of students. But anyways, this was a postponed session, and you guys must have attended other two sessions from the two other TAs. So no worries. So let's just start. And also, I'm not sure. Actually, I'm traveling next Sunday, so coming Sunday, that is the 17th of September. I'm traveling on that day, so I'm not sure whether I'll be able to conduct lecture on that day or not. But you will receive the communication from NPTEL team, and in case there is any postponement of the live session, you will receive an official email from the NPTEL team. So I thought I'll make that thing clear. So I don't think I need to share my screen. I can, since it's being recorded, I can directly go for PowerPoint. If some student join, and then I can share my screen. So to the people that might be watching the recording, you might feel I'm going slowly. That's the reason I've already explained. You can always increase the play speed to 1.5x or 2x, whatever suits you. So actually, it's quite difficult to have a live session without any audience. But anyways, so let me just give the introduction once again. So my name is Musab Rafiq. I'm a PhD student in the Department of Electrical Engineering at IIT Kanpur. This is live session 7 of the course of Digital Circuits. The course is taught by Professor Shantanu Chattopadhyay from IIT Kharagpur. So today we will discuss questions related to sequential circuits, mostly based on the flip-flops and some of them based on these counters. So towards the first question of today's live session, so let me just put this here. So question one states, what is the output signal that is Q here, frequency for the following circuit with 5 megahertz clock signal. So we are given this circuit and we are required to find out the output signal frequency, given that the input signal is 5 megahertz. So if you carefully examine, just even if it's mentioned also T, it's a T flip-flop, but this is a T flip-flop made up out of D flip-flop. Just a second, I guess someone wants to join the meeting. So I welcome you to this live session 7. Actually, I had started, so no worries, I'll start again. So today we'll discuss problems related to week 7, and let me just share my screen. Just a second. Yes, I'm showing this. Just a second. Something. So let me just give my introduction first. So my name is Mr. Rafiq. I'm a host for this course Digital Circuits that is taught by Professor Shantanu Chattopadhyay from IIT Kharagpur. I'm a PhD student in Department of Electrical Engineering at IIT Kanpur. Today we are going to discuss questions related to week 7. So here's this first question. The question states that, am I audible and is my screen visible? Can you just confirm? So this is the first question of today's live session. It states that what is the output signal frequency for the following circuit with 5 megahertz clock signal? So if you carefully examine the circuit, it's a T flip-flop. Even the symbol denotes it's a T flip-flop. But in the past lecture, you have seen that it's a T flip-flop made up out of D flip-flop, where the output Q and T are given to the XOR gate and then passed on to the input of the D flip-flop, and the overall circuit acts as a T flip-flop. So it's a T flip-flop, and we know that for T equal to 1, there is a toggling condition, and we have toggling at the output. That is, output changes at every rising clock edges, since it's a positive edge triggered flip-flop. Now what we have here is we have this input clock frequency of 5 megahertz. So F in is equal to 5 megahertz. Just a second, someone wants to join the meeting. Sorry about that. That was another person. So as I already said, this is a T flip-flop with the toggling condition. So Fn is equal to 5 megahertz, and for t equal to 1, there is a toggling, and for that case, we will only find the this, or should I say, the output clock frequency. So given is t equal to 1, and for f out then will be equal to f in by 2. Actually, it's 2 raised power n, since n is equal to 1, so it's f in by 2. That is 5 by 2, and f out will be equal to 2.5 megahertz, right? So this 2.5 megahertz, but it's for t equal to 1, because toggling only occurs for this case. So the overall answer for this circuit would be output signal will have a frequency of 2.5 megahertz for t equal to 1. That is this option. Any doubts? If not, we can move forward to question number 2 of today's live session. It says that modulus value of a 5-bit ring counter is. So we need to find the mod value of a 5-bit ring counter. So it's a ring counter where the output of the last flip flop will be connected to the Q. That is, Q will be connected to the input of the first flip flop. And for a ring counter, we know that mod n is equal to, that is the n modulus is equal to n, where n is the number of flip flops, right? So what we have here is mod n for a ring counter is equal to n, that is the number of flip flops, and n is equal to 5-bit. There will be 5 for a 5-bit ring counter. There will be 5 flip flops. So that implies number of flip flops is equal to 5, and that implies the mod value of this thing will be equal to 5. So a 5-bit ring counter has a mod value of 5. So you can write 5 here. Now we have this question. This is a really good question. So the question states that write the contents of the following registers. Write the contents of the following registers Q4, Q3, Q2, Q1, and Q0 for 3 clock transitions. So we need to write the contents of the following registers, that is Q4, Q3, Q2, Q1, and 0 for 3 clock transistors, and the assumption here is that all the values of the flip flops are initially at logic 1. So what we have here is, I'll just make a table. 1, 2, 4, 5, it's only 6. 6 plus 4, 6 plus 5. So I'll make a table, and this will also give me the contents of the register for 3 clock transitions. So what we have here is clock, then I will have Q4, then Q3, then Q2, then Q1, and then Q0. Clock is first. I write it now. This is the initial clock. So initially all the registers are at 1, 1, 1, 1. Now let's examine the circuit. So what we have here is we have these two tappings at Q1 and Q4, right? So the output of these registers at Q1 and Q4 are given to the input of the XOR gate, and the output of the XOR gate is then connected to the input of this flip flop or register, this D flip flop. So what we have here is, so Q1 as per these conditions, that is 1, and Q4, that is 1. So the input of the XOR gate will be 1 1, and for XOR gate input with 1 1, output is 0. So that implies D input to this 0th D flip flop will be 0. That implies Q0 will be 0 for clock transition 1. So it will be 0. Then all other will have 1 1 1 and 1, because input to them are 1 1 1, because previously Q4, Q3, Q2, Q1 1 1, right? Now what we have here is, so let me just make it bold to avoid any confusions. Now the clock transition 2 second, I should write second, and here I should write first. Now for second, so for second, the tapping Q4 is 1 again, and Q1 is also 1 again. So Q4 and Q1 are 1 again. So that implies Q input to Q0, D 0th register will be 0, D flip flop will be 0. So that implies it will be 0 only. And Q0 was 0 in the previous clock cycle, and now it's input to the first D flip flop, so it will be 0. And these three will be 1, 1, 1, right? Now we have the third clock cycle. Here the tapping Q1 is 0 and Q4 is 1. Q4 is 1 and Q1 is 0. So that implies input the XOR gate will be 1. That implies Q0 will be 1. Input to the second flip was 0, and input to second was also 0, and these two were 1, 1. So these were the contents of the registers for 3 clock transitions. First it was 1 1 1 1 0, then it was 1 1 1 0 0, then it was 1 1 0 0 1. So this is the required solution for the question. Any doubts in this question? If not, we can move forward to question number 4. Anytime you feel there are any doubts, you can just interrupt me because right now the audience is pretty low, so there is no issue. You can use your microphone, chat box, anything you like. So with a limited audience, you have that much liberty. Now, we'll move forward to question number 4. So actually, I marked this question for you guys to do first. So let me just read this question for you. Then you'll do the solve it, and then I'll show the solution. So this is the question. It says that which of the following output sequence, that is Q2, Q1, Q0. Remember the ordering. Sometimes while doing these questions, we forget about the ordering. So you might do the question rightly and write Q0, Q1, Q2. MSB, LSB kind of mix-ups, and you get the wrong answer. So you should be careful with these ordering also. So you need to write the output sequence, that is Q2, Q1, Q0, produced by the following flip-flops circuit. So I suggest you guys do it first, then I'll show the solution. It's a simple question. I'll give you 3 4 minutes. It will be done in 3 4 minutes. Then I'll show the solution. But do it. It will help you. It's a pretty easy question. Once you have the right answer, just type in. You have a couple of minutes, and then I'll show the solution. So now let me just show you the solution. So we have these three flip-flops that are T flip-flops, and what is happening here is at the input we have this one. So toggling will happen on all the negative edges. So why I'm saying negative edges? Because it is given, and also you can see it from the symbol. We have this bubble in front of this arrow, so that implies talking that it is a negative edge triggered flip-flop. And also t is equal to 1, so we have a toggling condition. And for clock, the output q0 is connected to clock of the t flip-flop, and q1 is connected to q2, this clock. So what I'll do, I'll first write here is clock. I'll make a clock waveform. So these spacings are equal. Ignore my this drawing. Then I'll have q0, q1, and q2. So what I'll assume here is their initial state is 0, 0, 0, 0, 0, and 0. And let me just draw these things. It will help me. So Q0, the toggling will happen at the negative edges. So it will be somewhat like this. Now I'll mark the negative edges of this thing. Now toggling will happen at the negative edges of these because the clock to Q1 is Q0. So right here, and for this it's right here. So initially it was 0, 0, 0, then it was 0, 0, 1, then it was 0, 1, 0, then it was 0, 1, 1. So my transitions are 0, 0, 0 to 0, 0, 1 to 0, 1, 0. Remember, I'm writing Q2, Q1, Q0, the order that is given in the question. And finally, it's 0, 1, 1. So this is the order. And if you can see, this is option A. Option A is the correct answer. Also remember here we made an assumption Q0, Q1, Q2 is 0, 0, 0, but you can also try it for 1, 1, 1, and you can see that for 1, 1, 1 the answer is different and that is not present in the option. You can do it as an home exercise. I have done it. So when you assume 111, none of the two options are correct. So for 111, that sequences are 111, 000, 001, and none of the options given here is that one. So option A is the right answer. Any doubts? Are you guys following? So are you guys following? So Mukesh, you wrote no, sir. Any doubts? You have any doubts? Okay, I guess it was related to the question. You don't have any doubts, so that's nice. So, okay, yeah, I got it. Now, towards what should I say? Question number 5 of today's live session. It states that what is the minimum number of flip-flops required to design a mod 150 counter? Just a second, someone wants to join the lecture. So, question number 4 states that what is the minimum number of flip-flops required to design a mod 150 counter? So you know that mod n counter, for a mod n counter, we have this condition: mod n counter should be less or equal to 2 raised to power n, where n is the number of flip flops. So if you want to design a mod n counter, So the number of flip-flops required is 2 raised power n. So the mod n should be less or equal to 2 raised power n. As per the game condition, mod is n is 150. So 150 should be less or equal to 2 raised power n. And as you can see, for n equal to 7, it's 128. 150 is not less than 128. For n equal to 8, we have 256. 2 raised power n will be equal to 256. So that implies n is equal to 8 is the minimum number of flip-flops required to design a mod 150 counter. So option A is the right answer. Now towards question number 6, I would like you guys to do first. I really want you guys to do this first, and then I'll show the solution. The question states that what is the output QA, QB, QC, QD? Remember the sequence QA, QB, QC, QD. What is the output sequence of the following circuit after 5 clock transitions? Assume initial state of the flip-flops are logic 0. So you have this question at hand. So it will not take more than 5 minutes. So I'll give you this 5 minutes, and then you can write your answers. And then after that, I'll also show the solution. Just a second, I'll turn on the lights. It's a really good question. Please do it. After 5 clock transitions, I think you forgot one transition. So let me just show the solution. So what we have here is, let me just draw the table. So 1, 2, 6, 7, 7. So here we have clock. Then we have QA, QB, QC, and QD. First, we have the initial state, and for that we have 0, 0, 0, 0. Then we have the first clock transition. So let's examine the circuit. So these are T flip-flops, and input of the T flip-flop A, that is this one, is Q bar, that is QT bar. So QT bar means 1, so toggling will happen, so it will be 1. QB is 0, so it will maintain its state. QC is 0, it will maintain its state, and QD is 0. Input to QD is also 0, it's all maintain its state. Now we have second. So Q bar will again be 1, so toggling will happen, it will be 0, and QB input to this flip flop is 1, so toggling will happen. This is 0, and this is also 0. Now third, QA again toggling will happen, this will be 1. QB input was 0, it will be remain at 1. QC input was 1, so toggling will happen, that is 1. And 0, 1, 0, 0, 1, 1. And this one is what should I say? 0, because QC was 0. Now fourth, fourth, it will be it will be 0, toggling will happen, it will be 0, toggling will happen 0, 0, and also the toggling will happen, it will be 1. So after fifth 5 clock transition, so this is 1, 2, 3, 4, 5. After 5 clock transitions, the so what should I say? The states of these flip flop is 0, 0, 0, 1. That is first this one initial, second, third, fourth, and fifth. So this is after fifth clock transition. The inputs is 0, 0, 1. So that is option A is the correct answer. So some people want to join in. Let me just admit them. Actually, I myself had doubt regarding what here is fifth transition. If we consider this first transition, then it's 5, otherwise it's 4. Anyways, the what should I say? The technique is like this only. There can be confusion. I myself have a doubt regarding what is the fifth transition, but as per the solution that I have referred to, it considers this as a fifth transition because these are mostly previous year questions and we are giving these solutions. But ignore the solution, just remember the procedure, how you have to approach it. So I think initial clock pulse is also considered here, 5 clock transitions. Otherwise, we need to consider one more transition. So if we consider that one, it will be 1, 0, 0, 0. Then it will be 1, 0, 0, right? After this, if we consider this as well, let's just say this thing, it will be 1 because toggling will happen. No, it will be 0, 0, 0, and QD will be 1. Okay, right, it's fine. Yeah, so yeah, it's correct. Yeah. So fifth transition. So see, if you carefully examine this fifth clock transitions, yeah, if you carefully examine this fifth clock transition, so QD was 1, so Q bar will be 0, so it will maintain its states. This QC will also maintain its states. This will also maintain its states because of the input QA. This will also maintain its state because QB is 0, and this will also maintain its state because QC is 0. So after fifth clock transition, it will be 0, 0, 0, 1. Yeah, it's right. You got my point? Actually, I also got confused right here, but it's 0, 0, 0, 1. Yeah, it's correct. So after fifth clock transition, the output will be 0, 0, 0, 1. Any doubts? So If not, we can proceed. Is it clear? Actually, there was some confusion, so that's why I'm asking again. Is it clear? Okay, I'll assume there are no doubts. In case there are any, you can always uh, interrupt me and ask anything. So now we have question number 7 of today's live session. It states that what is the output and the state of the circuit represented by the following state diagram for input sequence 111. So we are given the state diagram and we need to find out the state and the output, and also we are given that the circuit is initially in state A. So what we have here is initially we have this in state A, and we need to find out the logic and the state in which we for the following circuit for the input sequence 111. So we are at state A and we are given this input 1. So we are given this input 1 and we are at state A. And as you can see from the state diagram, once we are in state A and the input is 1, we go to state B with output as 0. Now I'm at state B and my input is again 1. So I'll make a transition to state C with output 0. Now I'm at state C and my input is again 1. So referring to the state diagram, I'll be in state C only and my output will be 0. So for input 111, I'll be in state C and my output will be 0. So state C and logic 0 will be my correct answer. Any doubts? So now let's discuss. This was question number. What was this question number? Question number 7. Now let's discuss question number 8. Question number 8 asks us to find the mod value of a 5-bit Johnson counter. This is a pretty simple question. You guys know that for a Johnson counter, that is also twisted ring counter, where for this last flip-flops output Q bar is connected to the input of the first flip-flop. So for a twisted ring counter or Johnson counter, modulus value is given by 2 into number of flip-flops, and it's 2 into 5, and that thing is equal to 10. So the mod value of this thing is 10. It is a pretty simple question. Now towards question number 9, just a second. Towards question number 9, it states that the current state of QA QB of two system two JK flip-flop system is 0 0. So we are given this initial state. Current state means here is initial state. Identify the sequence produced by QA QB. So I also mentioned this thing at the start to some of the students that were not present. To the some of the students, I try to repeat it again to the students who were not present at that time. So always remember the sequence QA QB. Sometimes we do the things correctly and we write QB QA instead of the QA QB that question is demanding. So what we have here is we have two JK flip-flops, right? And both and this first flip-flop, let's just term is the A flip-flop, is given as input 5 volt. 5 volt means 1 high. So JA and KA are always at 1, so they will always be a toggling condition. And J and JB and KB are simply equal to QA bar. Now what we'll do is we'll write a clock here, then I'll write QA, QB, and here slightly far away from this, I'll write QB, QA bar, sorry, I'll write QA bar. So clock first, clock pulse initial, we have 0, 0. That means QA bar is 1. So that implies JB and KB equal to 1. So toggling will happen. So QB will be 1. And also QA, again toggling will happen because J and K are always 1. So for first clock pulse it is 1, 1. Now for second clock pulse, so it was QA equal to 1, so QA bar will be 0. So QA bar will be 0, so that means JB and KB equal to 0. That means it will maintain its previous state, so it will be 1. And here toggling will happen. For QA, toggling will be happening always because it's connected to 1. Then they again add this thing, this will be 1 and this will be 1, so toggling will happen. And then I will have this thing as, what should I say, 0, and this will be 0 because it will maintain its state because QA bar was 0. So my sequence will be 0, 0, then 1, 1, then 0, 1, then 1, 0, then 0, 0, and it will again follow 1, 1 then. That's quite obvious. So this is my sequence 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1. So this is option C. Any doubts in this question? So let's move forward to question number 10 of today's live session. It says that consider the circuit shown below in the figure, right? So if you can see this circuit below, it's a T flip-flop with inputs coming out from the output of a OR gate. So it's an output coming out from a OR gate with inputs as Q and Q bar. So if you carefully look at this, this is connected to this and this is connected to this. So input is simply Q plus Q bar. And what will be this thing? This will always be equal to 1. So that implies a toggling condition. So there will be toggling at the output always. So, and if you know, when we have a toggling condition, my output frequency will be f by 2. So f in, which was 10 kilohertz, that means for f out, that is f out will be equal to f in by 2, because number of flip-flops are 1 only, so it will be 10 by 2, it will be 5 kilohertz. The only thing here was to figure out that it is a toggling condition, t equal to 1. Otherwise, you have seen a lot of questions these types, and it's quite trivial from that point. So it is option B. Now, I don't think there will be any doubts in this question. Even if there are, you can always ask me. Now, this is a question 11. I would like you guys to do first, then I will show you the solution. It states that which of the state diagram represents the following circuit. So you are given this circuit and you need to find out which of the state diagram correctly represents this circuit. So you guys do it first, then I'll show the solution. It will take hardly 5 minutes. So it's 6:47. I expect your answers at around 6:52. So I'll just show the solution after a couple of minutes. Till then, you can do this question and type in your answer when you are ready with your answers. So let me just show you the solution. I hope you guys did it. So what we have here is we are given this circuit and we need to find out the which of the state diagram correctly represents the following circuit. So this is a D flip flop and the output then is connected to the select this input line first and the Q bar is connected to 0 and we have the select line A. So let's just assume I'm at Q equal to 0 and A equal to 0. That implies A equal to 0, this will be selected and be given at D. So if A equal to 0, that means Q bar will be given to D. So that implies there will be a transition from Q equal to 0 to Q equal to 1 because it was connected to Q bar. So this will be for A equal to 0. And when A equal to 1, it is connected to Q only, so it will be at same state because it was at 0, it will remain at 0. Similarly, when Q equal to 1, A equal to 0, Q equal to 1, A equal to 0, that means Q bar is equal to 0, it will make a transition to Q equal to 0 for the case A equal to 0. And for A equal to 1, it will remain at Q equal to 1. So option D is the correct answer. So this was one way of doing it. Other way of doing it is, let's just say Q A equal to 0. So that means A equal to 0, this D will be connected to this thing, and A equal to 1, this D will be connected to Q only. So for 0, it will make transitions and for Q A equal to 1, it will remain the same state. That is A equal to 0, transition is happening. A equal to 1, no transition is happening. That was one other way of looking at this. So option D is the correct answer. Any doubts? Yeah, sure. So you are given this circuit, just a second, you are given this circuit and you need to figure out the state diagram. So this is a D flip-flop and you know the output of D flip-flop is equal to the input. So it will this D flip-flop. So and then it's connected to the mux, 2:1 mux. Q is connected to X1 and Q bar is connected to X0. So that implies for A equal to 0, this D will be connected to Q bar, and for A equal to 1, this D will be connected to Q. Now let's just say I'm at Q equal to 0 and my A is 0. So that implies this D will be connected to Q bar. So for the transition will be from Q equal to 0 to Q equal to 1. So that's what I've written here. And now let's suggest this A equal to 1. If A is equal to 1, D will be at Q. So Q was 0, it will remain at 0. So that's what I have done here. Similarly for this Q equal to 1. Q equal to 1, when A equal to 0, it will be connected to Q bar, so it will be going to 0. And when A equal to 1, it will remain at Q equal to 1. That's what I have drawn here. Other way of looking at this is, when A is equal to 0, this D is connected to Q bar. So it's making a transition always. And when Q equal to 1, A equal to 1, D is connected to Q. So it will always be at the same state. That was the other way of looking at it. So is it clear or are there any doubts? Okay. So now this was question number 11. Now we have question number 12 to discuss. So question number 12 asks us, for a given state table of a sequential circuit, the initial state AB of the circuit is 0, 0. So we have an initial state that is 0, 0. What will be the output sequence for the given input sequence 1, 1, 1, 0, 0? So we are given the state table and we need to figure out the output, what should I say, the output sequence. So let's just examine the state table first. So we have this present state right here, then we have this X, then we have this next state, and then we have the output Y. So for two we have 8 combinations because inputs are input can be 0 and 1, and then we have the next state and the output. So initially we are at what state? We are at 0, 0. Yeah, it's given in 0, 0. So present state is 0, 0. Then I have my input, then I have the next state, and then I have the output. So X is 1. So my present state is 0, 0 and X is 1. So my present state is 0, 0 and X is 1. The next state will be 0, 1 with output as 0. Refer this thing. We have to refer table every time. So I was at 0, 0, my input was 1. Now I'm at 0, 1 and output is 0. Now I'm at 0, 1. My input is again 1 because of this thing that is given. I am at 0, 1 and my input is 1. Now I'll be at 1, 0. Now I'll be at 1, 0 with output as 0. Then I'll be at 1, 0 with input as 1. 1, 0 with input as 1. Then I'll be at 1, 1 with output as 0. Then I'll be at 1, 1. Yeah. Yeah. For fourth. Yeah. See. Input sequence is 1, 1, 1. So what I have written is 1, 1, 1. Now the input will be 0 as per the given sequence. So I am at 1, 1 with input as 0. So I'll be at 0, 0. Next state. and output will be 1. And for final case, I'll be at so the final case I'll be at 0 0. So excuse me for this thing. I'll be at 0 0. My input is, what is my input? 0. My output will be 0 0. Sorry, my next state will be 0 0, and my output will be 0. So the output frequency is 0 0 0 1 0. So this is my output frequency 0 0 0 1 0. That is option C. So any doubt? So I guess your doubt was cleared, yeah? Okay, and that's fine. So now moving forward to question number 13. So moving forward to question number 13, it states that in the following counter, if the following counter is initially at 0 0 0 state, then after 6 clock ABCD will be, so ABCD are just the outputs of the D flip flops, and we need to figure out what will be the output. So I am at what I am at? I am at clock. So I'll just write the clock. Then I have the outputs A, B, C, D. So this is I should write first initial. So 0 0 0 0. Then my first clock pulse. So let's examine the circuit first. So this D, that is the input, is connected to this thing. So it's 0 0 0. So D bar here will be 1. So this thing will be 1. So it will be 1. Or then all others will be 0. Why? Because this was 0, this was 0, this was 0. Now the second clock pulse, it will be 1 1 0 0. Then it will be 1 1 1 0. Third, then it will be 1 1 1 1. Now what will happen? This was 1 1 1. D bar will be 0. So this will be 0. It will be 0 1 1 1. And after 6 clock pulse, so it will be 0. This 0 will pass to this. So it will be 0 0 1 1. So after 6 clock pulse, my output will be 0 0 1 1. That is option second. Can you guys tell me what is this circuit an example of? Have you seen this type of circuit? This has a name, if I'm not mistaken. Or am I missing? Yeah. Johnson's counter, yeah. So now let's discuss question number 14. So we have this question number 14. It states that the following state diagram represents which of the input equation where DA denotes a D flip flop with output A, the X and Y are inputs to the circuit. So we need to find out the equation for the following circuit. So how will we you let's make a state this table. So A here represents the input to the D flip flop. X, Y are, so A represents the states, that is Q. This is simply QA. You can write it as QA. This is X, Y are the inputs. So I'll write all the 8 cases: 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So my state is 0, A equal to 0, and my input is 0 0. My state is 0 and my input is 0 0. I'll remain at 0. My state is 0, my input is 0 1. I'm making a transition to 1. Refer to the state diagram. Now I'm at 0 and my input is 1 0. I'll make a transition to 1. Now I'm at 0, I have 1 1 as input, so I'll make a transition to 1. Now I'm at 1 and my inputs are 0, 0. I'll remain at 1. Now I'm at 1, my input is 0, 1. I'll remain at 1. I'm at 1 and my input is 1, 0. I'm making a transition to 0. And my state is 1 and my input is 1, 1. I am remaining at 1. So this was the table for this. Now we can use K-map and get the minimized equation. So this is A and this is your XY. Apart from these two, all other are 1. So we can make a chord like this, then appear like this, and appear like this. So my output equation will be dA will be equal to the term coming out from this chord is 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0. So it is Y plus the term coming out from this is AX bar, and the term coming out from this is A bar X. And if we can further minimize it, not minimize it, write the simpler form, it's Y plus A XOR X. So that is option C. Any doubts in this question? Is it clear? Okay, thank you. Now towards the next question. That is question number 15. I would like you to do this first. You guys should do this first, and then I'll show the solution. It will not take more than 3 4 minutes. So the initial state of the flip flop, this circuit is 1001. Remember the order A B C E 1001. How many clock cycles taken by the circuit to reach to 0110? You need to figure out how many clock cycles are required to reach to the state 0110. So you guys do it first, then I'll show you the solution. I see some of you have done it. That's nice. So now let me just show you the solution. So what we have here is this circuit where this output of this flip-flop is connected to the input of this flip-flop, and they all share a same clock. So we have this clock, and then we have this initial state A, B, C, E as 1001. So this is 1001. Then after the first clock pulse, so this is 0, so it will be 0, then it will be 1, then it will be 0, and then it will be 0. So this was first, then second, so E will be 1, so it will be 1, then this thing will be passed on 1 0 1 0, then this thing it will be 0, so it is 0 1 0 1, then this thing it will be 1, then it will be 0 and 0 0. So I messed up somewhere, so it will be 1 0 1 0, then it will be 1 1 0 1. Yeah, it will be 1 1 0 1, then it will be this 0 1 1 0. So it is 2 3 4. Only thing is happening, so here the transition is being made by this E bar, and all other things are getting passed on similarly. So after 4 clock pulses, we are having the state 0 1 1 0. Now, now towards the 16th question of today's live session, it states that in the given circuit, frequency of clock signal is 12 kilohertz. The frequency of signal at Q1 is, so we have this clock signal frequency. Now we need to figure out the frequency at Q1. So if we carefully examine this circuit, we have this D2 that is equal to Q1, and we have this D1 that is equal to AND of Q1 bar and Q2 bar. So Q1 bar and Q2 bar. And since we have to make the frequency, we have to find out the frequency, we can make an assumption that they are at initial frequency of what should I say, 0 0. They are at initially at 0 0. Now let me just draw the waveform for the clock. The spacings are not equal. You can ignore that thing. We need to just find out the frequency. And these are positive edge to it, right? So then we have Q1 and then we have Q0. So this is 0 and this is 0. Now refer to D2. D2 is equal to Q1. D2 is equal to Q1. Sorry, so this was Q2. This was Q2 and this was Q1. D2 is equal to Q1, so it will be 0, right? And Q1 is Q1 bar dot Q1 bar, so it will be 1 here, right? Now let me just draw these lines, it will help me. I have just made an assumption that Q2 Q1 are 0 0 initially. Yeah, you can do for anything. Your final answer will be same for all the cases. If you say 0 0 0 1 1 0 1 1, since you are only concerned with the frequency, your answer won't change. So this is right here, so it will make a transition. Now I'm at this thing. Now my Q1 is 1, so that means D2 is equal to 1, so it will make a transition right here. And this thing will be 0 because Q2 is 1, Q2 bar will be 0, so this will be 0. Now I'm at this thing. Now my D2 is equal to Q1, which is 0, so it will be 0 like this. And Q1 is Q1 bar dot Q1 2 bar. Q2 was 0. Q2 was 1, so Q2 bar will be 0, so it will be 0. Then D2 is called Q1, which was 0 again, so it will be 0. And what should I say? This thing Q2 Q1, now Q1 is 0, Q1 bar will be 1, and Q2 bar will also be equal to 1. So this will make a transition. So this was this is T, 2T, and 3T. So Q1 is having a time period of 3T. So F in is equal to 1 by T, and FQ1 is equal to 1 by 3T. That implies F in by 4, and F in is equal to 12 because it is given 12 kilohertz divided by 4. So my answer will be sorry, divided by 3. So my answer will be 4 kilohertz. That is option D, 4 kilohertz. Now towards the next question, that is 17th question of today's live session. So the towards the 17th question of today's live session, it states that what is the mod value of below counter? So I would like you guys to do this question first, then I will show you the solution. So just find out the mod value of the following counter. Okay, now let me just show you the solution. So this is A, this is, let's just term it as 0. Okay, so this is 0 given. So J0 equal to K0 is called to count enable, and that is 1. So it will always be in toggling condition. Then J1 equal to K1 is equal to A0 dot CE, that is AND operation. Then J2 equal to K2 is equal to AZ1 A0 CE, and J3 is equal to K3 is equal to A2 A1 A0 count enable. Now we have the clock here. This is initial state. Then I have A3, A2, A1, A0, making an assumption they are all at the initial states of 0, 0, 0. Here count enable is 1. So for first clock pulse, it will be 0, 0, 0. J0 is equal to K0 is equal to 1 because of the count enable is 1. J1 and K1 will be 0 because A0 is A0 or 0, and so it will be 0, 0, 1. For the second case, it will be 0, 0, 1, 0, because J0 equal to K0 equal to 1 is for all cases, so it will toggle. And A1 is J1 equal to K1 is equal to 1, so it will make a transition to 1. Then for the third clock pulse, it will be 0, 0, 1, 1, because J0 equal to K0 is 1, so it will toggle, and J1 equal to K1 is 0, 0, because A0 dot CE will be 0, so that why it will remain the same state. Similarly, it will be then 0, 1, 0, 0, and then 0, 1, 0, 1, 0, sorry, it will be 0, yeah, 0, 1, so on up to 1, 1, 1, 1. And then what will happen? All of them will toggle to 0, 0, 0, 0. So we are back to the same state. And total, there are 16 states. So the modulus value of this thing will be 16. Any doubts? You need to just figure out the inputs, and then you would have done it easily, and you would get the trend, and you can just simply write down the answer. Now moving forward to question number 18th of today's live session, it states that for the circuit shown below, the clock frequency is F0 and the duty cycle is 25%. For the signal at the output Q of the flip-flop, we need to find out the frequency and the duty cycle. So let's first draw the waveforms for the clock. I'll use a new slide for this. I'll use new slide for this. So let me just draw the clock. Clock is F0 and the duty cycle is 25%. So that means for 25% of the time it is high. So we can construct a clock something like this. It may not be equal, but we can work out. Now we have a 2-bit binary counter. So 2-bit binary counter is like this: 0, 0, 0, 1, 1, 0, 1, 1. So this is MSB and this is LSB. So these are the clock pulses that will make transition. So you can see for every clock pulse, so for every you can say changing clock or rising edges of the clock, we have a transition at LSB. And after every second clock pulse, we have a transition at MSB. So we can draw MSB like this. So assuming at 0, 0, after every 2 clock pulses, there is a transition like this. And for LSB, it is somewhat like this. So sorry, it should be here, it should be here. Then here, then here, then here. Starting from this thing, we are starting from this thing. So if this was T, this is 2T. So you can just write this thing is 2T. So my LSB is having a frequency of 2T. So this is important. Sorry, the time period of 2T. So the frequency will be F by 2. Now my frequency for LSB is F by 2. And my JK flip-flop is connected to LSB, right? JK flip-flop being connected to LSB means I will have inputs like this: 0, 0 and 1, 1. So let's just draw the waveform for JK flip-flop, and that is the output Q. We have output Q, and let's just mark the rising edges. Assuming at Q equal to 0, it will change here, and then it will change here, and then it will change somewhat here. So this 2T was for MSB, and the time period for Q then will be 4T. So the frequency of FJK will be F by 4, and Fin was Fin was F0, so it will be F0 by 4. And as you can see, the duty cycle is 50%. For 50% of time it's on and 50% of time it's off. So the duty cycle is 50%. So 50% duty cycle, I should write it here, 50% duty cycle. So my answer will be A, option A, frequency of F0 by 4 and duty cycle of 50%. I'll repeat it again. So we have a clock that is on for 25% of the time, and from that we got this LSB waveform, and the LSB is having the frequency of F by 2. Then this LSB is given as input to JK flip-flop. It will be 00 or 11. And for 11, it will make transition, and for 00, it will maintain the same state. So I'm assuming I was at state 0, and at the rising edge of the LSB, it is making a transition, and then it will be 00. It will maintain its state because it's a JK flip-flop. At 00, it will remain at its previous state. Then it is making a transition to 1. So for 1, it will make a 1 1. It will make a transition, and then I'll have this thing. So this is having a time period of 40. That means a frequency of f by 4, and it's on for 50% time. So the duty cycle is 50%. Any doubts? If not, let's move forward to question number 19th of today's live session. So it states that for the circuit shown below, the which of the following sequence of the counter state? So we need to find out the sequence. So what we'll do, we need to find out the sequence of the counter state. So we have clock and initial state. Since all of the options are 0 0, we can assume a 0 0 state, and we need to write q1 q0. Remember this thing. Now I am having this first clock state, the first clock transition. So it is q0 plus q1. So my d0 is q0 plus q1 bar. So NOR gate operation. So 0 0, it's 1, so it will be 1, and this will be 0 only. Then it's 1, and q0 will be NOR operation between 0 and 1, it will be 0. Then it is NOR operation between 1 and 0, that is 1, and q0 will be was 0, then it was q1 will be 0. And then it's a NOR operation between 0 1, so it will be 0 only. And it is one, and this thing was 1, I guess. No, so I'm getting confused here. 0 0 0 1 1 0 1 0, and it was 0 0, basically 0 0. So how it's 0 0? q0 was 0, q0 was 0, so d1 will be 0, and q1 was 1, q1 was 1, q1 was 1, and how, let me just check it again. 0 0 0 1 1 0 1 0, right? Then it's an OR gate operation. Yeah, it's 0 0. Yeah, because the NOR operation between 1 and 0 is 0, it's 1 0, and this 0 got passed on to d1, it's 0 0. Then again it will follow the same trend. So it is 0 0, then 0 1, then 1 0, then 0 0, and then 0 1. So that is option B. Let me just repeat it again. I was at 0 0 initially, and my input to the NOR gate was 0 0. My output will be 1, so Q0 was 1, and this Q0 was input to D1, so it will be 0. Yeah, I'm repeating. Yeah, I'm repeating. Yeah, I'm repeating. So initially I was 0 0. This Q1 is input to NOR gate and Q0 is input to NOR gate. So 0 0 operation of a NOR gate is output 1. So I have written Q0 as 1, and Q0 is connected to D1, so it is 0. Now Q0 is connected to D1, so this is 1, and the NOR operation between 0 and 1 is 0, so it's 0. Q0 is connected to D1, so it is 0, and the NOR operation between 0 and 1 is 0, so it is connected to, so it is be 0. Now again this will be 0 here, and NOR operation between 0 and 0 is 1, so we have a repetition, and my sequence will be somewhat like this. Is it clear? Now towards the last question of today's live session, we have Which of the following which of the following sequence AB produced by the sequential circuit for the given input waveform, assuming the initial state AB of the circuit is 0, 0. So let's just examine so we have this input X here that is going to this NOR gate, NOT gate, and then the input to the X gate. So this is X bar. This right here is B, and then we have this XOR gate. So this right here is A, and this right here is X, right? And also these are the positive edge triggered flip flops. Now let's just make a state table out of this, and then we can write the whole thing. So I'll just take this my space because I want to use the same side. So P here means present state. So PS means present state. A B input means X. Then I have next state A plus and B plus. And here are my inputs J A K A J B K B. Initially, let's assume I'm not assuming, so it's given in 0, 0. So I won't assume anything. I will just make the table first. Then I will write down the sequence that is followed. So JA as per the circuit, JA as per the circuit is equal to QB, and KA is equal to AND operation between X bar and QB. Then JB is equal to X bar and KB is equal to X plus A, QA. Now my present state is 0, 0 and my input is X. That means A is equal to 0, that is QA. To avoid any confusions, this QA. QA is equal to 0 and QB is equal to 0. That means JA is equal to 0. KA is equal to X bar QB, that is 1. JB is equal to X bar, that is 1. And KB is equal to X plus QA, that is 0. X is 0 and Q is also 0. KA is equal to X bar QB, so this is 0 plus QA. KB is X plus QA. XOR, sorry, XOR. My bad, XOR, yeah. XOR. So KB is XOR QA. So it is X is 0 and QA is also 0. So 0 XOR 0 is 0. Yeah. So everything is same. Now my next state is JAK is equal to 0. So it will maintain its 0 and JBKB is 1 0. So it is 1. Then I have 0 0 and my input is 1. So only things will change is for JB and or JA will remain same. JA will be 0. K is X bar QB, so that means 0. JB is X bar, so that is 0. And KB is X XOR QA, so that is 1 XOR 0, that is 1. So it will be 0, 0. Similarly, you can follow this thing and I'll just write down the whole table. 1, 1. Then I have 1, 0. Then I have 1, 1. Then I have 1 0 1 1 0 0 1 0 0 1 1 1 0 1 1 1 0 0 0 1 1, and here I have 0 0 0 1 1 1 0. You guys can check it. I have done it, but if there are any mistakes, you can check it also. 0 0 1 1 1 0, and here I have 0 1. Here I have 1 0 1 0 1, then 1 1. Then 0 0, then 1 1, then 0 0. Now, towards the main part of the question, we need to find out the states for the following waveforms. Let me just mark the positive edges of the following because this is the important part right here. This I found was the important part. All other things were quite simple. So here is my first clock transition and my x is 0. So x is 0 and I'm at 0, 0. So I'm at 0, 0 and x is 0. I'm at 0, 0, x is 0. So I'm making a transition to, we only need to write the state, so I won't write any output. So 0, 0, I'm at 0, 0 and my x is 0, so I'm making a transition to 0, 1. X equal to 0. Main part here is I'm looking at this thing right here, value of x right here. This is the main part. So 0, 0, x is 0, I'm at 0, 1. Now I'm at 0, 1 and my x is 1. My x is 1. Now I'm at 0, 1, my x is 1 and my next state will be 0, 1 only. No, no, what I'm saying. I'm at 0, 1 and x is 1. I'm at 0, 1 and x is 1. My next state is 1, 0. This thing. I am at 1, 0 and my x is 0. I am at 1, 0 and x is 0. I am at 1, 0 and x is 0. I'll be at 1, 1. Now I'm at 1, 1 and my x is 1. I am at 1, 1 and my x is 1. I'll remain at 1, 1. So my sequence is somewhat like this: 0, 0, then 0, 1, then 1, 0, then 1, 1, and then 1, 1. So 0, 0, 0, 1, 1, 0, 1, 1, 1, 1. So option B is the correct answer for option A. Option B, I think. Yeah, option A, option A. Sorry, option A. Option A. Option A. Option A. Option A is the correct answer. 0, 1. It has not written the initial state, so it's 0, 1, 1, 0, 1, 1, 1, 1. So after 1, 1, so let's just say, so after 1, 1, my input is 0. My input is 0. Then I'll make a transition to 0, 0. So this was first, first, second, second, third, third, fourth, fifth, and sixth. So my answer is 0, 1, 1, 0, 1, 1, 1, 1, and then 0, 0. So option A is the correct answer. Main part what I found out in this question was this: they were not aligned. So when I did it initially, I thought they were aligned, but the main part here is the waveforms were not aligned. So X was making transition at different points, not according to the clock. That's the main point here. So you need to check the inputs at these points. These were the main point what I found out. Here X is 0, X is 1, X is 0, X is 1, X is 0, X is 1, 0, 1, 0, 1, 0. So option A was the correct answer. Any doubts in this question? If not, we can end today's live session. We will meet next week. I'm not sure on which date. Actually, I'm traveling on Sunday, so I'll inform the NPTEL team to kindly postpone my lecture. So you'll be informed accordingly. So my scheduled lectures are actually Sundays 30 to 5 p.m. But this week I was busy with some personal work, and next week I'm traveling on that date. So you'll get notification accordingly. So thank you for joining. See you next time.